Hi guys, this video is designed to give you a brief introduction to intermolecular forces. So let us get into it. All right, so when we have a sample of, for instance, we'll just use water as an example. Okay, we have really two types of electrostatic forces that are existing in the sample. The first electrostatic force that's existing in the sample are called intramolecular forces. Intra means inside. So intramolecular forces are the forces inside a molecule. Now these are the electrostatic forces. They can be the attraction between the electrons and the nuclei of the individual atoms, but also remember there are repulsive forces existing between the electron groups. So you have this group of electrostatic forces inside the molecule itself. However, when you have a sample of water, you never just have one water molecule. You always have nearby water molecules as well. There's always billions and trillions of them. So never think that there's just one molecule. You have lots of them. Here you have another force going on, which is occurring between the molecules. And these are called intermolecular forces. Intermolecular forces. Inter meaning between. Like an interstate highway runs between states. Intermolecular forces are between molecules. So let's give a little definition to intermolecular forces just based on that alone. These are the forces, and generally we are talking about attractive forces that exist between neighboring atoms or molecules, just depending on what you're talking about. Here, we are talking about a sample of water, which of course would be molecules, but say you had a sample of helium gas, those would be the intermolecular forces existing between atoms, because helium is just existing as an atom. So that's just a brief introduction on what does intermolecular force even mean. A couple bullet points about intermolecular forces, and from here on out, I'm just going to use IMFs. Meaning intermolecular forces. We'll kind of drop the intramolecular forces for now. The ones between are the ones we're focusing on in this video. Intermolecular forces, a couple things about them. These are significantly weaker than the bonding forces. Bonding forces are another word for the ones inside the molecule, the ones holding the molecule together. They are significantly weaker than bonding forces. And there's two reasons why they're weaker. Number one, they are weaker because they operate at greater distances. So if you can just picture an attraction between a positive and a negative particle, we'll just put it up here for now. Okay, this attraction would be far greater than this attraction. Okay, just because you are trying to operate at a greater distance. That relates to Coulomb's law, but we won't have to get into that for now. Just understand that intermolecular forces are weaker because they are operating at greater distances. I know it doesn't quite look like that according to my drawing, but it is a greater distance. But they're also weaker because they deal with partial charges rather than full charges. We'll get into that as we go into the specific types. So that's bullet point number one. Bullet point number two. Intermolecular forces are responsible for holding the condensed states together. Let me leave a little parenthesis here, together. Now, when I say the condensed states, you hear the word state, so you know we're talking about solid, liquid, or gas. Of those three, which ones are considered condensed? You hear the word dense in them. Which ones have the molecules tightly packed so that they're fairly dense? And the two condensed states are considered the solid state and the liquid state. It is intermolecular forces that are responsible for holding the solid and the liquid together. Take water, for example. When you have, what is the difference between ice and water vapor? You could call it steam. The issue here is the intermolecular forces. They are greatest in the ice, they're less significant in the water, and they're even less significant in the steam. So a last bullet point here is this, and it's related to this earlier bullet point. Intermolecular forces, IMFs, can be overcome with the application of heat. And everything can come straight back to ice, water, and water vapor. How do you turn ice into water? Well, you apply heat. Okay, and that's how the ice melts into water. What are you doing? You're not changing anything about the molecule itself. You're not breaking bonds. You are not rearranging any of the atoms. However, you are overcoming the intermolecular forces. Okay, and when those are overcome, the water can escape from the liquid and move off into the gas phase because it is now free from its neighbors. And so that is another aspect of intermolecular forces. They can be overcome with heat. Okay, so that's enough for now. So really what we want to get into are the 4 types of intermolecular forces. We're going to go through each type, learn a little bit about each, and show some examples. So these are going to be presented in order of increasing strength. So I'm going to start with the weakest type of intermolecular force and build to the strongest. So the first type of intermolecular force that we will talk about are called, sometimes you'll hear the London part, sometimes you won't in our book. They're just called dispersion forces. Sometimes you'll hear the word London dispersion forces. It's all the same thing. I've heard them called induced dipole forces as well. But we'll just go with dispersion forces. So these are the weakest type of intermolecular force. Actually, let me go ahead and just give you the list here, and then I'll have more on my board to go into each type. The second type of intermolecular force in terms of increasing strength are called dipole-dipole forces. The third type are called hydrogen bonds. I'm going to put bonds in parentheses. I'll explain why in a little bit. And the fourth type we will call ion-dipole forces. So this is the list in order of increasing strength of the attraction between the molecules. All right, so let me go ahead, just since this board is kind of small, let me go ahead and erase the list, and then we'll take these one at a time. So we're going to start with London dispersion forces. What are they? Where can they be found? And then drawing a picture. All right, so what are dispersion forces? Dispersion forces are the result from the instantaneous dipoles. I'll explain what all of this means as we move along. Instantaneous dipoles that occur as electrons move around the nucleus. There's probably a more eloquent definition from your book, but that just came from my head, so it's close though. All right, so this is best explained with a picture. So let's go ahead and draw 2 helium atoms. So helium atoms have, of course, a nucleus, and they have a 2+ nucleus. Okay, so what we have going on are 2 helium atoms here. And of course, you've got their electron cloud. Okay, so you've got their, sorry about that. So you've got their electron cloud. And you have 2 electrons in each helium atom. So we know that the electrons are living in the 1s orbital, and sometimes they might be on kind of opposite sides of the nucleus. Okay, let me just deal with this left atom for now. Just because they're moving around, and we don't even know exactly where they are at any one moment, but they might happen to be on opposite sides of the nucleus at any one moment. However, at any one moment, for really no apparent reason, they might happen to end up on the same side of the nucleus. Okay, now, what happens? There's really 2 things that happened as a result of that. Number 1, you will get what's called an instantaneous dipole. Instantaneous means instant, or fleeting to an extent as well, but it happens in an instant, and it frankly can be fleeting as well. And a dipole is any time you have a separation of charges, anytime like it's polar, where you've got a positive side and a negative side. So just looking at this atom right now, you have what's called a partial negative end, because the electrons are over here to the right. So this part of the atom, I'm forgetting about the atom for now. This part of the atom, the right side, this side here, is partially negative. Okay, this side is partially positive because the electrons, where all the negativity is, are over here. And so all you have is the effect of the nucleus on this side. So you have what's called a dipole. Okay, now what does that do to the neighboring atom? Well, this atom, where it had its electrons just doing its thing, if its electrons happened to be on this side, they would flee to the opposite side, because the last thing electrons want to be near is a negative charge or other electrons. So this atom would respond in kind and would adopt the exact same, well, a similar situation where his electrons flee to the other side, giving him also a partial negative on the side where the electrons are and a partial positive on the side where the electrons are not. Now, here you have the intermolecular force right here. That's your dispersion force, because you have an attraction between a positive and negative charge, and that's going to be an attraction, and it will hold these together to some extent. Now, because remember, this little curvy d stands for partial. You're not talking about a full-on negative charge, because the electrons are just on that side. Okay, they haven't been given or anything like that. So partial negative, partial positive. It's a very weak force. Okay, so dispersion forces. Let me make this point right here. Individually, if I'm talking about a single attraction, individually, these are very weak forces. Because they're just partial, they're instantaneous, they can come and go, they can leave just as easily as they started. So they're very weak forces. However, I like to compare them to something like Velcro. Okay, Velcro, as you know, has thousands of these little connections. Okay, so you have 2 pieces of Velcro that you're trying to stick together. You've got these little connections made of plastic. Each one of them is going to be fairly weak. But if you have hundreds or thousands, or frankly even 20, of little pieces of Velcro, each doing their part to attract the other side, you will end up accumulating a quite significant attraction. So while I have this, and this is true, individually these are very weak forces. Let's add this, but they accumulate. And you can add in your notes, like Velcro. Okay, so if you have a lot of them, they can become quite significant. Let me give you the bottom line here. Let me see if I can erase this. But they accumulate like Velcro. And let me go ahead and erase this so I can have my whole board here. In large molecules, actually, frankly, or large atoms, these can become very significant. They're going to be very insignificant in small molecules, but the larger the molecule, the greater the significance. Example, if you compare hydrocarbons, so hydrocarbons are molecules that contain just hydrogen and carbon in them. So let's have a small hydrocarbon like methane, CH4, just one carbon. Let's compare that to something like octane, which has the formula C8H18. But if you were to draw it, it would look like 8 carbons all in a row. 1, 2, 3, 4, 5, 6, 7, 8. And this methane would just have 1 carbon. Now, it would have all the hydrogens as well, but let's kind of try to keep things a little bit simple. And this would have hydrogens surrounding it as well, but we don't need to worry about that for now. So let's just deal with one thing at a time. Let's talk about the methane. The methane. When you are trying to look at how methane interacts with its neighbors, it will only have the potential, a small potential for dispersion forces because it's a very small molecule. So these are the dispersion forces. Okay, so it will have a fairly insignificant amount of dispersion forces. However, if you compare octane and how it reacts with its neighbors, or how it interacts with its neighbors, it has dispersion forces along the whole length of the molecule. Okay, now, why is this significant? Well, if you look at the phases of these two species at room temperature, methane is a gas. Why is it a gas? It's a gas because there's very little holding one molecule to the next, so they separate, and they're going to be far from each other. Octane is a liquid at room temperature. Why? Why is it a liquid? It's a liquid because there are significant intermolecular forces holding the species together, so it stays in a condensed phase. Okay, and you would have to add heat, quite a bit of heat, to separate it out and turn it into a vapor. So that is, I know that's a lot there, but bottom line, you need to know what dispersion forces are. You need to know that they act like Velcro in the sense that each individual dispersion force is weak. However, they accumulate along the length of a molecule, so in large molecules, they become significant. Last thing I should say, where can you find them? Dispersion forces are present anywhere you have electrons. And therefore, another way of saying that is that they are ubiquitous. Ubiquitous in Latin comes from the Latin words for everywhere all the time. So every molecule and every atom will display dispersion forces. However, the larger the molecule, the more significant they become. So hopefully I explained that good enough. That was the bit about dispersion forces. That probably will take the longest time out of all of them. The second type of intermolecular force, second in terms of strength, so these are the next strongest, are dipole-dipole forces. Now these are not ubiquitous. These are not found everywhere. These types of forces are present between all polar molecules. Polar meaning you have a positive and a negative end to the molecule. Classic example would be something like formaldehyde. Formaldehyde has a Vesper model that looks like this. Okay, it is a trigonal planar structure because the carbon has 3 effective pairs. 120-degree angles. Okay, so you can see that it's polar for, remember there's 2 requirements to be polar. First, you have to have polar bonds of some sort. The carbon-oxygen bond is polar. There's a significant difference in electronegativities between carbon and oxygen, with oxygen being more electronegative. Secondly, you need to have some asymmetry, okay? So even while the molecule does have a line of symmetry here across the middle, it does have asymmetry from north to south, okay? So therefore, you have a partial negative on the northern part of this molecule, northern just being in how I drew it, and a partial positive in the southern part of this molecule, okay? So it is a polar molecule. Now remember, when you have formaldehyde, which this happens to be, you don't just have one of them, you've got billions of them in whatever sample, and there will be a neighboring formaldehyde, and he will actually orient himself so that his partial negative end is near the partial positive end of the neighboring molecule because they're attracted. Positive things are attracted to negative things. So we have a intermolecular force right here, and that is your dipole-dipole force, intermolecular force, between the negative end of one polar molecule and the positive end of the neighboring molecule. So that is what a dipole-dipole force is. That's all we need to say about that one. Let's move on to hydrogen bonds. Now I'm going to put this in the bonds in quotation marks because I just want to make the point that hydrogen bonds are not, they're not chemical bonds, okay? So they are not, we cannot relate them to a single bond or a double bond or a triple bond. Chemical bonds that hold molecules together are significantly stronger than hydrogen bonds. However, that being said, for an intermolecular force, hydrogen bonds are quite significant and quite strong. You notice they were third on our list towards a list of increasing strength. What are hydrogen bonds? Hydrogen bonds, you can consider them the ultra, this is my word, but the ultra dipole-dipole force. So in terms of how they work, it's very similar to what we just had in the dipole-dipole bonds, and you'll see. But why are they ultra? Why do they kind of get this special consideration? So the classic example for hydrogen bonds comes from water. Water molecules form hydrogen bonds with neighboring water molecules. So we're going to get into this here. So here's one water molecule. Remember, it has a bent shape. And it does have a dipole where the partial negative is up near the oxygen because of the electronegativity of the oxygen. And hydrogen would have a partial positive. And so would this one. Okay, so remember there is a neighboring, there's always neighboring water molecules. I'll just draw the neighboring one down here. And he has the exact same situation. He also has a partial negative on his oxygens and a partial positive on his hydrogens. So you can see the interaction right here. There is an attraction between the positive end of one molecule, namely the hydrogen end, with the oxygen end of the neighboring molecule. And here is your intermolecular force, otherwise known as your hydrogen bond. So in terms of how it works, it's very similar to a dipole-dipole. It is a dipole-dipole force. But why is it ultra? Why is it special? Hydrogen bonds, let me make this a third bullet point, are formed between molecules that have a hydrogen. Obviously, it has to have a hydrogen or it can't form a hydrogen bond, that have a hydrogen bonded to a nitrogen, oxygen, or fluorine. Nitrogen, oxygen, or fluorine. Okay. So, and when I say hydrogen bonded to it, I'm talking about within a single molecule. So, in order to form a hydrogen bond, your hydrogen on your molecule has to itself be bound to an oxygen, okay, or a nitrogen, or a fluorine. in order to form a hydrogen bond with the neighboring molecule. So that the molecule must have, this is the requirement, in itself, a hydrogen bonded to an N, O, or F. That is a requirement. Why is that a requirement? What's special about nitrogen, oxygen, or fluorine are these are kind of like the top three atoms or elements for electronegativity. These are the most electronegative atoms, with fluorine being king, oxygen, call it queen, and nitrogen, call it jack. First, second, and third place. So why is that significant? Well, let's go here for a minute. Let's just focus on this water for a second here. There is a huge difference in electronegativity between hydrogen and oxygen. Because of that, the oxygen is not just partial negative, it's very partial negative. Okay, so I'm just going to put pretend numbers, but picture it being, rather than just being 10%, being 80%. That's totally pretend, but it's going to be a very, very big partial negative. And therefore, the hydrogen is going to be a very significant partial positive. In other words, there's a big difference in the dipoles. It has a very large dipole moment here. So because of that, this attraction is going to be even stronger, because it's not just an insignificant partial, it's a big partial negative attracted to a big partial positive. So that is why these are called the ultra-dipole-dipole force, because you have the hydrogen bound to these very, very electronegative atoms, N, O, or F. If you looked at the previous example that I gave you, formaldehyde, you'll notice, this was the previous example. Why was this one not a good example for hydrogen bonds? And the answer is because its hydrogens are bound to a carbon, not N, O, or F. The hydrogen must be directly bound to N, O, or F to qualify the molecule for hydrogen bonding. Okay, so that is what a hydrogen bond is. Now, when coming back to this example of ice melting into water, evaporating into water vapor, understand that's what you're breaking. When you melt the ice, you are breaking the hydrogen bonds. When you evaporate the water, you're breaking them even further and to an even greater extent. And you do that through the application of heat. Okay, so that's how you break those hydrogen bonds. So that is what we have to say about that. And then the last intermolecular force that we will discuss here is the strongest of all four, and these are called ion-dipole forces. You can tell what they are between just from the name itself. These are forces that occur. These are the attractive forces that occur between an ion, which of course is just a charged particle, but it will have a full charge, +1, -1, +2, -2, cation or anion, it could be either, that occur between an ion and a dipole on a neighboring molecule. Now, we've actually already seen these and used these in our chemistry. And you'll see my picture will look familiar, okay? Salt water, NaCl, aqueous. When we were first talking about electrolytes and dissociation and all this stuff, we had that there in the salt, there's cation, anion, Na plus, Cl minus, Na plus, Cl minus. That's what's in the lattice structure of the ionic compound. However, when it is in the presence of water molecules, which we know are polar, partial negative up by the oxygen, partial positive down by the hydrogen. Let me just put another one down here. I'll put this one upside down. They're floating around. They can turn. Partial positive near the hydrogen, partial negative near the oxygen. The reason that this ionic compound dissolves is because the anions, for instance, the chloride ions, will be attracted to the partial positives on the water. Why are they attracted? They're attracted because of an intermolecular force called an ion-dipole force. It's between an ion, which has a full minus charge, and the dipole on the water. And conversely, you will have an attraction for the cations for the oxygen dipole on the water. And here is the intermolecular force happening over here. So these are ion-dipole forces. Why are they the strongest? Well, they are the strongest because one of the charges involved in the attraction is a full charge, not a partial, not a fraction, but a full-on charge. Sometimes 1 minus, sometimes 2 minus, sometimes 1 plus, sometimes 2 plus, just depending on what your substance is. But these are the strongest of all the intermolecular forces. So that is that. If you just took notes on that, remember that dispersion forces are everywhere, found on everything. They operate, you can think of them operating like Velcro in that each one is going to be fairly insignificant, very weak, but they accumulate and become very significant across large molecules. And the best example that we can think of for large molecules are large hydrocarbons, like the octane, like the, remember, phospholipid bilayer. Okay, that is all dispersion forces. Okay, large fats, oils, all of these are examples of where dispersion forces are very significant. Dipole-dipole forces present in all polar molecules. Hydrogen bonds, a special type of dipole-dipole force present in molecules, or between molecules, as long as the molecules themselves have hydrogen bound to N, O, or F in the molecule. That creates a very significant dipole, which in turn makes a hydrogen bond with neighboring molecules. And then ion-dipole forces, the strongest of all of them. That's that. Hope that helps you prepare for your exam. Good luck. Bye-bye.